Hi everyone. In this video we'll continue our discussion of some of the counting principles that we can use for large problems. In the last video we talked about tree diagrams and the fundamental counting principle. In this video we will talk about permutations. Alright, so before we get there, there's one calculator key that you need to understand and know how to use, and that is the factorial key. Alright, so here's the definition, and if you want to take a minute to look for this on the calculator that you have, here are some options for you where you may find this. It looks like an exclamation mark. If you have a graphing calculator like a TI 84 or a TI 83 or 89 or something like that, there's a key, the math key, and then you should be able to scroll over to where you see PRB, which stands for probability, and then in that list you'll see the exclamation mark symbol for factorial. If you have a scientific calculator like a TI 30 or a Casio, then you may have a PRB key, not the math but just PRB, and if you press that, same thing, you should be able to find the key in there. If you're using a cell phone calculator, then sometimes the advanced panel, if you swipe to one side or the other, or turn your cell phone, you can see that factorial symbol. And if you have a different type of calculator, look for PRB for probability, or you may also just see this actual key on the main calculator keys themselves. If not, if you don't have that key, you can still do this type of symbol, but you'll just need to do the work by hand, so we'll talk about that as well. Alright, so here's a definition. This is a symbol that works only with natural numbers, so no negatives, no fractions, or anything like that. But for any natural number, n factorial just means multiply by every other counting number smaller than that, all the way down to 1. Right, so an example would be 5 factorial. If you have this key, practice using it. Okay, so just enter 5 and then that symbol. And this means 5 times 4 times 3 times 2 times 1. Okay, so you can see if you didn't have that key, then you would just write that out, work it out yourself using multiplication, and that would be 120. Two weird cases, 0 factorial and 1 factorial. Well, 1 factorial doesn't have any other counting numbers smaller than it, so you just stop there. Okay, 1 factorial is 1. And then 0 factorial, 0 is not a natural number, so it doesn't really fit this definition, but it shows up so often in counting problems that we really needed to know what this was, so we defined this to be 1 as well. And the reason is basically just that that's what works. In the counting problems, if you kind of do them the long way, listing out all of the options, and then do them using these formulas, it turns out that if you let 0 factorial be 1, then this formula does reflect the number of options that really exist. Okay, so let's practice 8 factorial. Alright, enter that on a calculator or do 8 times 7 times 6 all the way down to 1. And you should get 40,320. Alright, we can divide with factorials. So this would be, alright, try entering that in. You would just enter 12, the factorial symbol, then the division symbol, and then 10 factorial. If you're doing this by hand, this would be 12 times 11 times 10 all the way down to 1. Dot, 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 all the way to 1. Okay, over 10 times 9 times 8, etc., all the way down to 1. Alright, and notice what you get for an answer here. You should get 132. Alright, so here's what's going on, the math behind the scenes. Just like a normal fraction, this is big, but this is all one term. All of these numbers are multiplied together, and you're allowed to cancel in fractions, okay, reduce something in the numerator with a factor in the denominator. So these 10s cancel, the 9s cancel, 8s, 7s, 6s, I didn't write them, but 5s, 4s, 3, 2, and then 1 all cancel. So the only thing that you have here is 12 times 11 in the numerator, and that's the 132. Alright, so another way to write this, if you wanted to show this by hand but not have to write out all of those numbers, you could write this as 12 times 11 times 10 factorial, because that represents 10 down to 1, and then divided by 10 factorial. And so you see that we actually can cancel entire factorials as long as the number is exactly the same, 10 and 10, because that represents all of the counting numbers multiplied from 10 down to 1. Okay, try another one. How about 6 factorial divided by 5 factorial? Okay, and you should see that that equals 6. All right. So notice that 12 tenths reduced is 6 fifths, but notice that the factorials are different. So what that means is that you can't just reduce fractions before you do that factorial symbol. And the reason is because this isn't really a 12 and a 10, it's a 12 with all of these other numbers attached to it, and a 10 with all of these other numbers attached to it. Alright, so in short, you can still reduce as you normally did, just individual numbers that match, and you can reduce if the factorials match exactly, but you can't reduce numbers inside of that factorial symbol. Alright, so let's go on to our second counting rule, and we'll get back to the factorial notation in a minute to use that. But basically your counting rule here is a permutations, and a permutation is an arrangement of n distinct objects in a specific order. Alright, so let's look at an example. Suppose a photographer wants to arrange Carmen, Juan, and Christina for a photo. So first of all, let's list the ways he could arrange them in order, right, the number of permutations, and then we'll use the fundamental counting principle to see if our answer matches. Alright, so let's do a tree diagram. So our three choices, we're choosing the people to stand in the first, second, and third spots. Alright, so first we have, could be Carmen, Juan, or Christina. And then it is implied here that there's no repetition, so it doesn't actually say it, but if you think about it, these are people, so obviously somebody couldn't stand in two different places at the same time. So if Carmen's in the first spot, then the second person can only be Christina or Juan. Right? If Juan is first, then it has to be either Christina or Carmen next. And if Christina's first, then either Juan or Carmen. Now by the time you've chosen your first two people, that only leaves you with one person in each case that's left for that third spot. Okay, Juan here, Christina, and so forth. Okay, so here are all of the different options. And then if you count the branches at the end of the tree diagram, you should see that there are 6 different options. Okay, 6 ways to arrange those 3 people. Now let's try the same problem using the fundamental counting principle. Alright, we're choosing our 3 people. Well, we have 3 options for who could stand in the first spot. Then that leaves us with only 2 people to come next and 1 for the last spot. So multiplying, we get the same answer, still 6 people. Alright. Now think about how this problem would change if we had 5 people. And we won't make the whole tree diagram, but basically you would have 5 people who could stand in the first spot. Alright, so let's say it's like people A, B, C, D, and E. Alright, well then the second person, you've got 4 options left in each of those cases, etc. Then for the third person, you'd be down to only 3 people left to choose from. Alright, and so forth. And if you did the fundamental counting principle, this would look like your 5 people, 5 options, then 4 options, 3 people, 2 people, and then by the time you get to that last spot, you only have one person left who can stand there. Okay? So in other words, when we're arranging 3 people, we had 3 times 2 times 1 options, and when we had 5 people, there were 5 times 4 times 3 times 2 times 1 ways to arrange them. Right, so this should look sort of familiar. We just talked about this. This is a factorial. Right, this is 5 factorial, and this is 3 factorial. So here's the connection, why we learned that symbol. This is your second counting rule, permutations. The number of permutations of n distinct objects, like the people in our last example, using all of the objects, is n factorial. All right. Here's an example that was given at a faculty Christmas party I went to once. We were asked how many ways are there for Santa to arrange his reindeer in front of his sleigh, assuming that Rudolph is first. And the prize was a gift card, so here's a real-life application for where you would use this. But anyway, if you want to arrange the reindeer, all right, so you just need to know how many there are. There are 8 reindeer other than Rudolph. So this would be 8 factorial ways to arrange the reindeer. All right, 40,320 options. Some people started listing all of them out, and of course they did not win the gift card. Here's another example. In how many different orders can the 12 basketball teams in the Big Ten Conference finish? Seriously, there are 12 teams in the Big Ten, at least as of 2012. Okay, so you just need to figure out the setup, look at how many things you're arranging, and here they're not really like standing in a line, but this is still implied that there's some sort of an order because they're trying to finish in a certain order. All right, so it's 12 teams arranged in order, or 12 factorial, and this is a very large number, 479,001,600. Okay, and a final note about this factorial symbol. Your numbers won't get much larger than that for the examples that we'll do. Here's an example of one that is really large. Okay, let's say it was like 4,000 factorial divided by 3,999 factorial. Right? Well, notice if you put just the first number in your calculator, 4,000 factorial, you'll probably get some sort of an error. Your calculator can't handle that many digits. Okay, so you've seen that even just 12 factorial was already in the hundreds of millions. So picture how much bigger this number is. So your 2 options would either be to just enter the whole problem altogether, and then your calculator can handle something like that, or you can sort of simplify this by hand. So this is just 4,000 times 3,999, and all the other numbers down to 1. And then the denominator, we have 3,999 times all the other numbers down to 1. So most of this cancels, and the answer should be 4,000. Okay, so far in calculating permutations, we've used all of the available objects. But what if only some of them are selected? We can still use permutations. So let's say that you had a class of 20 people, and rather than arranging all 20 of them in a row, let's say that we just wanted to choose like 3 representatives, and maybe we're choosing them for like first, second, and third prize or something like that. Right, so that's sort of an implied order that's necessary. Okay, we need a definite first person and a definite second and third person. So it's kind of like arranging 3 out of 20 people, just not all 20 of those people. Alright, so we'll talk about that in the next video, and we'll stop there for now. So in this video you have learned the factorial notation, and then how to use that to find the permutations or arrangements of different numbers of objects.